Welcome to Why Rocks, a BYU Department of Geological Sciences podcast. We are pleased to have with us today Dr. Steve Nelson from the BYU Geology Department. Steve, how long have you been on the faculty at BYU?
This is my 27th year.
And before you came to teach at BYU?
I spent 4 years in the high-level nuclear waste industry in Las Vegas, Nevada, working on the Yucca Mountain project.
Yucca Mountain. How did that all turn? What did you do at Yucca Mountain?
I managed science programs at national labs, and I felt like a doctor changing bedpans.
No, Steve, come on. Tell us how you really feel.
So I was happy to get back into a teaching research role.
Oh, very nice. Now, what exactly do you teach at BYU?
I teach introductory classes. I really like introductory classes. I like to see students who come in a bit geologically challenged and defiant, it's kind of with the attitude, you can't make me like this, and then they end up liking it. And then I teach igneous and metamorphic petrology, and then I teach graduate courses in isotope geochemistry.
Now, geochemistry, is that your specialty, if that's the way we want to put that out?
I would say I was trained as an isotope geochemist.
How did that come about? How did you become a geologist? I guess maybe that's the first question. Did you go to school initially thinking, hey, I'm going to be a geologist?
Well, I'll try to keep the backstory short, but I thought I wanted to be an archaeologist, Indiana Jones, maybe pith helmet, khaki.
But it's so not Indiana Jones when you take the classes.
No, it's so not Indiana Jones when you take the classes. And I was actually a volunteer at archaeological excavations 2 summers in Israel in the 70s. But I got into the coursework, and I don't want to offend any of our friends in anthropology, but it just was not academically rigorous.
Boring. So
I thought, well, geology. I'd done well in junior high, and I grew up in Utah. These big mountains behind us, and we'd frequently travel to national parks, and I just wondered why do things look the way they do, and so that got me into geology. And
then how do you make the transition over to chemistry?
Well, chemistry is a tool. Really, you could say I'm an applied chemist. I apply chemical measurements to understand how the earth works.
Okay.
Rocks, soils, waters.
Very cool. As far as teaching your geochemistry classes, how many different classes do you teach?
I teach...
I guess I should say, have you taught?
I have taught geochemistry, which is the undergraduate course that's usually taught by Professor Bickmore or Professor Lamont now. But I have taught that. And then I have traditionally taught low-temperature isotope geochemistry and high-temperature isotope geochemistry, which are graduate courses. And now that we've hired Dr. Bergner, he's taken over the low-temperature course.
So for the people listening, even though they might be alumni of our department or maybe people who are just tuning in and don't know much about geology, the difference in those two courses, why is there a low-temperature course and a high-temperature course?
Okay, that's a great question. For a low-temperature course, we would be using... when we back up, both of these courses are really toolkit courses that you learn to use a bunch of tools. And at low temperatures, the low-temperature course, you learn how to interrogate, if you will, water, sediment, maybe lake sediment in bogs, ice. So things that are isotopic techniques that we use to study things that are at or near the Earth's surface and at sort of ambient temperatures. High temperature, we're looking at igneous processes and metamorphic processes, which occur at high temperatures and high pressures.
Okay. And so the students not the same students likely then wouldn't take both of those classes.
Usually not, but some want a good solid background, and so some will take both. But usually they'll take one or the other.
Okay, so somebody going into mining, high temperature would be more appropriate.
Absolutely.
And then someone taking the low temperature would likely go into
groundwater consulting, groundwater studies consulting,
okay.
A regulatory environment,
Okay.
something like that.
So a number of your students go into groundwater or environmental type jobs, etc.
Absolutely.
So does your research then follow that same line? Do you do more high temperature research or more low temperature research?
Anymore, I do almost exclusively low temperature research, and so I'm pursuing lines of research that'll help students not go into the mining industry, but go into environmental consulting and environmental regulation areas.
Okay. One of those areas of research took you to Hawaii about 10 years ago, I think. You started making trips to Hawaii to look at a number of things. And what drew you to Hawaii, besides the obvious?
Well, it's Hawaii. I've never had trouble convincing students to do field work in Hawaii.
Wendover, Nevada, or Hawaii? How did you make the choice?
Yeah, well, in 1998 we had a departmental field trip to Hawaii, and it was aimed mostly at looking at active or recent volcanism. But we made a stop at a location just north of Hilo, where water is pouring out of a lava tube into a stream and then into the ocean.
That would just be spectacular.
Yeah, and students and some faculty who will remain nameless were immediately in the water. But it occurred to me that there's dissolved material in that water that is removing mass from the Hawaiian Islands 24/7, 365 days a year.
One atom at a time.
One atom at a time. And so I got interested. This sparked this idea. How do the Hawaiian Islands go away? Volcanoes build them. Now how do they go away? And so I've worked on water and soil in the Hawaiian Islands beginning about 2008, and I'm kind of starting to wrap that up.
What have you discovered? What has the research led? What kind of publications or knowledge have you gained from that?
I can mention a couple of things. One is that if you've ever been to Hawaii, or if you've ever seen pictures or TV shows that are set there, they're these big canyons. And so you think, well, the islands are eroded by streams. And I don't want to downplay the importance of streams, but actually the islands erode primarily by reacting with ground and surface water, dissolving material that was in the lava, and then that material is carried to the ocean. So it's more accurate to say the Hawaiian Islands are dissolving than they are eroding.
So we need to put a big umbrella over them.
That's right.
So we can preserve the tropical paradise.
That's right. And then the other thing is I've begun working with a group of microbiologists at National Jewish Health in Denver. They're a pulmonary disease hospital. And one of my colleagues, Jennifer Honda, has recently moved to the University of Texas at Tyler. And it turns out that Mycobacterium, this is a genus that includes leprosy and tuberculosis. But there are other species in the genus that cause disease, usually in immunocompromised individuals. And we've been looking at how, where, and why these microorganisms live in the environment in Hawaii. Although these are rare infections, they do infect humans, and the rate of infection is 4 or 5 times higher in Hawaii than it is on the mainland.
Wow.
So we want to understand where they're living in the environment and how people are acquiring infections.
So you're not just saving the planet, you're saving the population.
We're ultimately trying to help people, and the ultimate goal is to try to come up with some predictive tools that will help people at risk decide where to live, and if they want to live in Hawaii, where in Hawaii the risk is lower.
And if you have to go to Hawaii to do this research, that's a sword you're willing to fall on.
I'm willing to carry that burden.
Now, more recently, kind of on the same theme, you made your way to another volcano out in the ocean.
Yes, this one is in the North Atlantic, and it's Iceland. And put Iceland on your bucket list. It is amazing. And what I'm doing is essentially the same kinds of studies, but in a different climate. So we want to see how rates and processes differ due to being in a much colder place than a warm tropical place like Hawaii.
What have you found so far?
We have found the biggest discovery so far is that most of the mass leaves the Hawaiian Islands in groundwater that discharges directly into the ocean. It flows through the subsurface of the island. In Iceland, there is very, very little groundwater recharge, and most of the mass is removed in streams.
So it's sediment, or is it dissolved as well?
Dissolved and suspended sediment. So it's both stuff that's dissolved in the water as well as particles. They're about equal.
Are the dissolved concentrations in Iceland similar to the volumes you would see in Hawaii?
Yeah, the dissolved amount of dissolved material in Iceland is similar to what we see in Hawaii. And the reason is most of the soils in Iceland have glass in them. The Icelandic soils are developed on volcanic ash mostly, and that glass in the volcanic ash is very reactive. And so based upon the climate alone, you'd predict that Iceland would have less dissolved stuff in the water, but it actually has about the same amount because it's reacting with glass rather than crystals.
Now, you have also done work here locally in Utah, down south of campus. There's a place that I know you've taken students to called the Black Rock Desert. Similar geology, basalt flows, as Hawaii and Iceland. Have you done similar type investigations there?
Yeah, I have a student who's currently working on some fossil spring deposits that we think are hydrothermal. But we've also done, in collaboration with John McBride, we've done some seismic reflection studies and combined coring to look at lake sediments, but especially volcanic features that have been disrupted by faults in the last couple of million years.
Okay, very cool. To change gears just a little bit, we've talked about the volcanoes and the trips to Iceland and Hawaii. Tell our listeners what a diatom is, if you would, please.
Oh.
You see the smile that just came across his face?
Thank you, Randy, for asking that question. Diatoms are a form of algae. They're not strictly plants, but they photosynthesize. And diatoms are everywhere. They're in soil and in lakes and in streams, and they produce by photosynthesis, about 30% of the oxygen we breathe.
30%?
Yeah.
So we're breathing some diatom excrement right now.
Yes, diatom O2.
Okay.
Yeah, every time you take a breath. And they build their shells, their cell walls, out of glass. It's pure silicon dioxide. We geologists would call it opal.
Okay.
And they're very highly ornamented. And the diatoms you find in lake sediment tell you a lot about the environment in which they were living. In fact, they scream it at you. And because they're made out of opal, they're very well preserved. And so we can work out past environmental histories from cores, lake cores, Lake Bonneville, Farmington Bay, Utah Lake, wetlands that we've investigated, to tease out how the lake chemistry has changed or how the climate has changed, whether it's been wetter or drier, whether there was the water was brackish or fresh. And the diatoms just scream this at you, and they're beautiful. They're beautifully ornamented, and you look at them under the microscope, and you move the slide under the lens, and then all of a sudden this magical thing appears in your eyepieces.
Now, you said microscope. Are these not fossils that our listeners can just go out to Farmington Bay and collect a bucket full?
They can, and if, as a matter of fact, almost everyone who listens to this has interacted with diatoms. If you have stepped on a slimy brown film on a rock in a stream or at the shore of a lake,
The kind that make you land on your butt.
exactly that kind.
Okay.
That is that's a biofilm of diatoms.
So they're killing the diatoms.
Yes, and they're so we've all encountered them. If you look in a lake and you see a plant and it's got like feathery brown stuff growing off it, those are diatoms.
Oh.
So they're all over the place. They're in the ocean, they're in fresh water. Some will live in soil or mosses, and they just scream at you what the conditions were like when they were growing in a core.
Where have you sampled diatoms from around the county, the state, the country, etc.? Where have you done this type of research at?
Predominantly in Lake Bonneville sediment cores from Pilot Valley. And then we have looked at the water history from pioneer times to the present in both Farmington Bay and Utah Lake, using in part diatoms. And then we've done it down in the Fish Lake Plateau near Capitol Reef. There's a wetland down there where we reconstructed about a 13,000 year climate record, and we could tell when it was wetter, when it was drier, when it was standing water all year round versus when it would dry out in the summers.
How much variability do you see?
Enormous.
So goes wet, goes dry, goes wet, goes dry.
Yes, and the diatoms respond. And the nice thing about diatoms is they reproduce rapidly. So when there's a change in the environment, there's a change in the diatoms present almost immediately.
Now, you didn't mention the Great Salt Lake. Are there diatoms in that?
There are diatoms in the Great Salt Lake, but they'll be mostly restricted to the south arm. The north arm is too saline.
Okay.
To have many diatoms. They will live up to maybe 3-4 times the salinity of seawater rather, but there's a kind of an upper limit to what they'll take.
And you see similar patterns throughout the state. So if it's getting wetter in Farmington Bay or the Great Salt Lake, is it also getting wetter in southern Utah?
That's a tough question to answer. I would have to have a lot of samples from a lot of different places that I'd analyze to make those comparisons.
Okay, so we need more diatoms. So if you're listening at home, head out someplace and fill up a bucket of brown slimy stuff and bring it to Dr. Nelson.
Yeah. Yeah. Most of my studies are retrospective, and I'm looking at histories at one place rather than comparing histories at a single moment in time across multiple locations.
Okay. So I'm going to read this next little part, just because there's no way I could memorize it, and I'll probably pronounce some of it wrong. Our producer, Kevin, has provided me with some sample questions that I could ask Dr. Nelson, and one of these I just have to pull up. It's talking about equipment that you use. And can you tell us what a Finnegan MAT Delta Plus Stable Isotope Ratio Mass Spectrometer is?
I can tell you.
I need a break.
That's a mouthful. and remember, ChatGPT generated that question.
Yes, ChatGPT generated that question. Thank you, ChatGPT.
That instrument has been decommissioned.
Okay.
But we use instruments, successor instruments, one of which we have in our laboratories.
And what is that called?
That is called
the whole thing. Don't spare.
A Thermo Delta 5.
Well, that was anticlimactic.
Yeah. It's not quite. It's not quite as yeah. And we use these to measure a lot of the isotope ratios that we then use to understand whatever it is we're trying to understand.
Okay, so what kinds of isotopes can you feed into this machine?
We feed in gases, and so we can measure isotope ratios of carbon, nitrogen, oxygen, hydrogen, and sulfur. Everything has to go in as a gas, so we can measure carbon and oxygen on CO2.
Okay.
Nitrogen isotope ratios on N2 nitrogen molecules, hydrogen 2 molecules for hydrogen. Everything has to be in a gas.
Gotcha. So no solid material. Do you use the mass spectrometer that you feed solid material into as well?
I do. We don't have any of those on campus, but I do some of that sort of work currently up at the University of Utah.
Okay.
They have a laboratory that we have access to at their internal rates, and so we measure isotope ratios of things like strontium and isotope ratios of uranium and other analytes to. Yeah.
Okay, so all of the mass spectrometers on campus are gas mass spectrometers?
Oh, I'm sure there are other mass spectrometers on campus, especially in chemistry, which
can
accept either liquid or solid sources. But in our department, we have one mass spectrometer, and it only accepts gases.
Well, and there's a reason that we only have one. Steve, what's the price tag on that machine?
That price, the equivalent instrument, if it were purchased today with all the sort of bells
and whistles. I want the radio and the map screen and everything.
About $500,000.
Only $500,000.
Yeah.
Yeah. So we should get them in different colors.
Well, right. you can coordinate with your lab coat.
That would be fun. We're going to go back for a second to something that we talked to you brought up at the very beginning. You teach Geology 101. In fact, you teach Geology 101 every year. Sometimes you teach it fall semester and winter semester. What do you, over the course of your career, what do you enjoy about that class?
I did mention it, but I'd like to maybe reiterate on a little bit and expand. A lot of students are taking that class because it checks off a box in their GE. And some students, you'll never be able to get them excited about geology, but a lot of them you will. Some will even change their major, but some won't, because they decide they want to do something else, which is great. But
the world has to have a few accountants as well.
It does, but I frequently run into people that say, "Yeah, I took Geology 101 from you." And I get a lot of good feedback that said it's changed the way I look at the world. And I know that a 101 student, 10 years later, they're going to have forgotten 95% of what they learned.
Including the name of whoever taught their class.
Yeah. Well, Steve Nelson, they'll either remember it or they can't remember it. It's such a common name. And I digress.
But that's okay. That's what we're here for.
But they will remember that the subject was interesting, that they liked it, and I think that they will retain that attitude, that positive attitude towards science, and then I think they'll instill that in their family, in their children.
Generational knowledge.
That's right.
All right. In your undergraduate level geochemistry class, what's kind of the overview curriculum for that? What are the students, what are they going to take away from that class after sitting through 42 hours of Steve Nelson?
Well,
it seems different when you put it that way, doesn't it?
Let's remember, and this may get edited out, I'm not the one who usually teaches it, but what they learn in that is basic thermodynamics. It is a lot of the same material that they learned in Chemistry 105 and 106, their basic college chemistry, but it's applied. And so what it gives them the opportunity to do is to see how geochemistry, or the chemical principles they've learned in other classes and they're relearning again in this class, work in the real world. It gives them a concrete foundation largely in thermodynamics.
Okay. To kind of come to today, how does the drought that Utah has experienced over the past number of years, not this year particularly, How has the drought shown up in your research, or does it?
It has shown up in our studies, in particular in Farmington Bay. I mentioned that we had looked at diatoms and cores in Farmington Bay. We were also looking at nutrients like phosphorus, which cause harmful algal blooms. Climate change and is increasing the risk for harmful algal blooms in our local lakes. Utah Lake, Farmington Bay, and the Great Salt Lake.
These are the big red toxic algal blooms that we seem to get more rampant every summer.
But they're not red. They're blue-green.
Okay.
Blue-green algae.
There was a dog, I think, a year ago that got killed by swimming through one.
Yeah,
of those.
they produce neurotoxins, so they can kill livestock and people. There's some evidence that the toxins accumulate up the food chain, and when the algae bloom, they deprive indirectly aquatic life of oxygen, and so they'll kill fish and other organisms. And so that's a real problem. And when water levels decline due to drought and it's warmer due to climate change, these algal blooms are likely to be more frequent and more intense.
Dr. Nelson protecting the public yet again.
That's right.
Do you see evidence for other droughts like the one we're kind of in your research as we go back over that 13,000 year period of time you mentioned?
Yes. When we go back to this small wetland in the Fish Lake Plateau, we see that from about 13 to about 10,000 years ago, the climate was wetter than it is today, but it was more volatile. It was wetter on average, but there were extreme swings. And then from about 10,000 years to about 3,000 years ago, the climate was actually drier than it is today.
So that would have been the mother of all droughts.
Yeah, it would have been drier. And then the beginning about 2,500, 3,000 years ago, the climate became wetter. And that's the climate we're used to now, however, with a drought superimposed upon it. And so things returned to wetter conditions and more stable. So, we can absolutely see the influence of drought and cycles of drought and wet and dry periods, again, using the diatoms.
Diatoms. I'm wondering, and I wish I had numbers for you, but I'm wondering at this point in our podcast, this episode, how many of our listeners have Googled a diatom to see how spectacularly intricate and beautiful those pictures are?
I hope it's 100%.
Oh, I hope so too. You were actually going to the department had talked about getting a really high-end 3D printer a number of years ago, and I remember being in faculty meeting, and your take on it was that we should get the best one we could get, because then you could 3D print diatoms.
Right, and you actually, in order to do that, to generate the 3D file to print, you have to use the electron microscope and orient the sample at different angles and from different perspectives, and then we can, in essence, do what's called photogrammetry and reconstruct the 3D surface and then print it. Brooks does this with bones.
Right.
That's how he documents digitally the three-dimensional structure of bones and dinosaur bones, and we can do the same thing with diatoms.
But you haven't done that yet.
I haven't done that yet.
Oh, come on. It sounds like a labor of love waiting to happen.
It is, but we're busy.
So there's quite the elaborate 3D printer just outside of this room. Looks kind of like a Buckminster fullerene molecule. You could use that to print some diatoms.
Absolutely, I could. I would. I would, with some effort, need to go to the electron microscope and take some pictures of diatom cell walls at different angles.
But you'd have to orient them under your really elaborate optical microscope in your office and then take them down?
No. I would go down with a mount prepared for the electron microscope, and they have done this before, where they want to create three-dimensional data. of very, very small objects. So they do that directly in the electron microscope. It's the same technology that that Brooks Britt uses for photographing and reconstructing digitally dinosaur bones. As I was coming up here, one of our graduate students took drone images of lava flow surfaces in the Snake River Plain in Idaho, and he was printing out from the drone footage three-dimensional images of the surfaces of the lava flows.
Very cool.
Yeah.
That's outstanding. Now, when you take these samples down to the scanning electron microscope, they have to be kind of spray painted, for lack of the correct terminology, with gold. Is that right?
You can gold coat them.
Because then you could make really, really tiny jewelry for your wife out of them.
That's right. Yeah.
Look what I got you, honey.
You're hitting a sample with an electron beam, and so the electrons have to be able to be conducted away. And so one way to do that is to use gold coating. But our particular instrument will also admit a very, very, very small amount of water vapor, and the water vapor will conduct the electricity away. So you don't have to gold coat, but you do get somewhat better images if you do.
Okay.
Yeah.
I unfortunately did a lot of conodonts in my master's thesis, so I'm familiar with the process to some extent.
Yeah. It's a much newer instrument, and you don't have to anymore.
Oh, very nice. I'm too old. If you looked back at your career at this point in time, and we're going to put you on the spot, and maybe it's something you've already told us, and that's totally fine. What is one thing from your career that you are extremely proud of?
I would say that it was a line of research that I haven't really pursued recently. It kind of wrapped up about 2014. But it was looking at the way that groundwater moves through the subsurface in the western United States through limestones. And Alan Mayo, an alumnus, and I conducted a research program that challenged some of the prevailing wisdom. And we're starting to see that bear fruit in publications. There's an idea of interbasin flow, that water just flows through limestones right under mountain ranges to underneath another valley and through another mountain range. And we challenge that, and that people are beginning to take a second look at that, and that's probably a highlight.
So is interbasin flow actually happening?
We think that interbasin flow is not happening to the extent that other researchers have claimed it does.
And the epicenter for this research, is that this legendary place out on the Nevada border, a place of scenic beauty and wonder called Pilot Valley?
No, it's another valley. It's Death Valley.
Oh, the mother of Pilot Valley.
That's right. There are publications that you could go and look at in the scientific literature that claim that water that falls on mountain ranges outside of Ely, Nevada, that's east central Nevada.
The cultural mecca of Ely, Nevada.
That's right. That it makes its way and ultimately discharges to the surface in Death Valley.
All the way from Ely.
Yes.
So eastern Nevada to western Nevada.
To actually
Eastern California.
Southeastern California.
Wow, that's hundreds and hundreds of miles.
Yeah. This idea of that water flows like that, there was good evidence in the 60s and 70s to back it up. But we challenged it. We looked at some specific studies. We conducted some specific studies to look at the propensity of the overall geologic evidence, and we discovered that it's really not happening to that extent, and others are beginning to acknowledge that.
So from a water rights standpoint or groundwater law, How remarkable is this realization?
It's really remarkable because there's a saying, I'm borrowing this from Alan Mayo. Water flows downhill or towards money. And if interbasin flow is real, let's imagine we have a mountain range and valleys on either side. If I pump groundwater out of one of the valleys, if interbasin flow is happening, I could be stealing water from a water user in the other valley on the other side of the mountains.
Kind of like the premise that has been put forth. Nevada, Las Vegas has a well field just on the southwestern tip of Utah in Nevada. And there's a lot of people in Utah that think Nevada is stealing Utah's water.
Right.
So maybe not stealing as much as we would have historically thought.
That's right. Not stealing as much as we would have historically thought, but they may be developing what is ultimately a smaller resource.
Gotcha. Very, very cool. Very cool. Death Valley, definitely the mother of Pilot Valley. Pilot Valley's scenic and beautiful, but nothing says die in the heat like Death Valley.
Yeah, in Furnace Creek, next to the Funeral Mountains when it's 123 degrees.
If there's a place called the Funeral Mountains, it just gives you an idea of what's going on there.
That's right.
Yeah. All right, we're gonna ask you a couple of really quick, more personal questions as we tidy this off today. What are some things that you personally enjoy besides researching diatoms?
I have recently taken up landscape painting. I'm a dilettante. My teacher is Bob Ross.
Very cool.
But
have you seen the movie?
I have not seen the movie. But I know a little bit of the backstory. You know, Bill Alexander and Bob Ross. Yeah. But I enjoy landscape painting, and I have a friend who said, if I'd known how great grandkids were, I'd have had them first. So I like spending a lot of time with my grandkids.
Very cool. That's why your grandkids all need to listen to the podcast. Now, you also, from what I understand, are quite the expert glass blower.
No, that is not true.
It is so true.
It is not true. I took a scientific glass blowing class at the University of Utah about 15 years ago.
You are the only person that I know personally who has ever blown glass.
And I learned two things. One is I'm not a scientific glass blower. And the other thing is that hot glass looks just like cold glass.
Oh.
When you go to pick it up.
Was that a painful experience?
Yes.
Oh. There you have it, folks. That's just the high point to end on. We have been very pleased to visit with Dr. Steve Nelson, professor of geochemistry in the Department of Geological Sciences here at Brigham Young University today. And this has been a BYU Department of Geology podcast. Why Rocks? Thanks for joining us.